a vast expanse that stretches beyond the limits of human imagination. Its scale is almost incomprehensible, with distances measured not in kilometers or miles, but in light years. The distance that light travels in 1 year, approximately 9.46 trillion kilometers. Even within our own galaxy, the Milky Way, which spans about the sheer vastness of space defies easy understanding. Beyond the Milky Way lies the observable universe, a region stretching some 93 billion light-years across, containing over 2 trillion galaxies, each with billions or even trillions of stars. The immensity of the universe. To truly grasp the scale of the universe, one must understand the concept of a light year, which represents the distance light can travel in 1 year. Given that light moves at a speed of about 300,000 kilometers per second, a single light year encompasses nearly 9.46 trillion kilometers. Even at this incredible speed, it would take light 100,000 years to traverse the Milky Way, our home galaxy, which contains an estimated 200 to 400 billion stars. Beyond our galaxy lies the vast expanse of intergalactic space, where galaxies are separated by millions of light years. The Andromeda Galaxy, the closest spiral galaxy to the Milky Way, is located about 5 million light-years away. These distances are so immense that they challenge our ability to comprehend them. They are far beyond the scales we encounter in our daily lives. The observable universe. The observable universe refers to the portion of the cosmos that we can observe, given the finite speed of light and the age of the universe. Light from the most distant objects we can see today has traveled for over 13 billion years to reach us. This means that when we observe these distant galaxies, we are looking back in time, witnessing the universe as it was billions of years ago. The observable universe is about 93 billion light-years in diameter, containing an estimated 2 trillion galaxies. Each of these galaxies can host anywhere from millions to trillions of stars, with countless planets orbiting these stars. The diversity of cosmic structures within the observable universe is staggering, ranging from tiny dwarf galaxies to massive galaxy clusters, some of which span millions of light-years. Beyond the observable, the unseen universe. But the observable universe is only a fraction of the entire cosmos. What lies beyond the limits of our observation is a subject of speculation, with some theories suggesting that the universe could be infinite, with no boundaries at all. This notion of an infinite universe raises profound questions about the nature of reality, space, and time, challenging our most fundamental assumptions about existence. If the universe is indeed infinite, it means that there could be regions of space far beyond our observational reach, where the conditions might be vastly different from those in our local universe. Some cosmological models propose the existence of a multiverse, a collection of parallel universes, each with its own unique physical laws and constants. In such a scenario, our universe would be just one of many, each with its own distinct characteristics. The idea of an infinite or multiverse also introduces the concept of eternal inflation, a theory that suggests the universe underwent a rapid expansion shortly after the Big Bang. In this model, different regions of space could have stopped inflating at different times, leading to the formation of multiple disconnected bubble universes within a larger multiverse. The dynamic and multi-layered complexity of the universe. The universe is not a static backdrop, but a dynamic and ever-evolving entity. From the smallest subatomic particles to the largest galactic superclusters, the universe is a tapestry woven from countless layers of complexity, each contributing to the grand cosmic symphony. The intricate interplay of forces and particles at different scales gives rise to the rich diversity of structures and phenomena we observe. The quantum realm, the foundation of all matter. At the smallest scales, the universe is governed by the laws of quantum mechanics, a branch of physics that describes the behavior of particles at the atomic and subatomic levels. In the quantum realm, particles such as electrons, protons, and neutrons exhibit both wave-like and particle-like properties, and their behavior is governed by probabilities rather than deterministic laws. One of the most intriguing aspects of quantum mechanics is the concept of superposition, where particles can exist in multiple states simultaneously until they are observed or measured. This phenomenon is illustrated by the famous thought experiment known as Schrödinger's cat, where a cat in a sealed box can be considered both alive and dead until the box is opened and the cat's state is observed. Another key feature of quantum mechanics is entanglement, a phenomenon where particles become interconnected in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance separating them. This spooky action at a distance, as Albert Einstein famously described it, has been experimentally confirmed and remains one of the most mysterious aspects of quantum theory. The quantum realm is the foundation of all matter and energy in the universe. The interactions of fundamental particles, such as quarks and leptons, give rise to the atoms and molecules that make up the world around us. These particles are governed by the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Understanding these interactions is essential for unraveling the mysteries of the universe's smallest scales. The classical realm, the laws of motion and gravity. At larger scales, the behavior of matter and energy is governed by the laws of classical physics, particularly Isaac Newton's laws of motion and Albert Einstein's theory of general relativity. Newton's laws describe how objects move and interact under the influence of forces, while Einstein's theory revolutionized our understanding of gravity by describing it as the curvature of space-time caused by massive objects. General relativity predicts phenomena such as the bending of light around massive objects, known as gravitational lensing, and the existence of black holes, regions of space where gravity is so strong that not even light can escape. These predictions have been confirmed by numerous observations, including the recent detection of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, such as merging black holes. The interplay between quantum mechanics and general relativity remains one of the greatest unsolved mysteries in physics. While both theories have been incredibly successful in their respective domains, they are fundamentally incompatible when applied together, particularly in extreme environments like the interiors of black holes or the conditions present at the beginning of the universe. The quest to unify these two pillars of modern physics into a single, coherent theory of quantum gravity is one of the most important challenges facing physicists today. The cosmic web, the universe's large-scale structure. Beyond the quantum and classical realms lies the complexity of astrophysical objects and structures. Stars, planets, and galaxies are formed through processes that involve the interplay of gravity, nuclear fusion, and electromagnetic forces. These objects, in turn, are part of even larger structures, such as galaxy clusters and superclusters, which are connected by the cosmic web, a vast network of dark matter filaments that spans the entire universe. The cosmic web is the large-scale structure of the universe, composed of filaments of dark matter and galaxies that stretch across vast distances. These filaments are the result of billions of years of cosmic evolution, shaped by the force of gravity acting on the initial fluctuations in the density of matter that emerged from the Big Bang. At the intersections of these filaments lie galaxy clusters, the most massive gravitationally bound structures in the universe. Galaxy clusters contain hundreds or even thousands of galaxies, along with vast amounts of hot gas and dark matter. The study of galaxy clusters provides valuable insights into the distribution of dark matter, the nature of dark energy, and the processes that drive the formation and evolution of galaxies. The cosmic web also reveals the hierarchical nature of the universe's structure, where smaller structures are nested within larger ones. For example, galaxies are composed of stars, planets, and gas, while galaxies themselves are part of larger clusters, which in turn are part of even larger superclusters. This hierarchical structure is a key feature of the universe's complexity, reflecting the interplay of forces and processes at different scales. The mysteries of dark matter and dark energy. One of the most profound mysteries in modern cosmology is the nature of dark matter and dark energy, two components that together make up about 95% of the total mass energy content of the universe. Despite their prevalence, these components remain largely invisible and undetectable by conventional means, making them some of the most enigmatic aspects of the cosmos. Dark matter, the invisible scaffolding of the universe. Dark matter is thought to be responsible for the gravitational effects observed in galaxies and galaxy clusters that cannot be explained by the visible matter alone. It acts as a cosmic scaffolding, holding galaxies together and influencing their rotation rates. Without dark matter, galaxies would not have enough mass to prevent them from flying apart, given their observed rotation speeds. The nature of dark matter remains one of the greatest unsolved mysteries in astrophysics. While it does not interact with light or other forms of electromagnetic radiation, its presence can be inferred from its gravitational effects. Several candidates have been proposed for dark matter, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, but none have been definitively detected. The search for dark matter is a major focus of current research, with experiments designed to detect dark matter particles directly, indirectly through their decay or annihilation products, or through their interactions with ordinary matter. Understanding the nature of dark matter is crucial for unraveling the mysteries of the universe's structure and evolution. Dark energy, the force driving the universe's accelerating expansion. Dark energy is the force driving the accelerated expansion of the universe, a discovery that was first made in the late 1990s through observations of distant supernova. This acceleration was unexpected and has profound implications for the fate of the universe. Unlike dark matter, which is thought to clump together and form the scaffolding of the universe, dark energy appears to be a property of space itself, acting as a repulsive force that counteracts gravity. It makes up about 70% of the total energy density of the universe and is responsible for the observed acceleration in the expansion of space. The nature of dark energy is one of the most pressing questions in cosmology. Some theories suggest that it could be related to the cosmological constant, a term that Albert Einstein originally introduced in his equations of general relativity. Others propose that dark energy might be a manifestation of a new field or force that we have yet to understand. The continued study of dark energy is essential for understanding the ultimate fate of the universe and the fundamental forces that govern its evolution. The evolution of cosmic structures. The universe's complexity is not static. It has evolved over billions of years, giving rise to the structures we observe today. The formation of galaxies, stars, and planets is the result of a long process of cosmic evolution that began with the Big Bang and continues to this day. The birth and evolution of galaxies. In the early universe, matter was distributed almost uniformly, with only tiny fluctuations in density. These fluctuations grew over time due to the force of gravity, leading to the formation of the first stars and galaxies. As galaxies formed and merged, they created larger structures, such as galaxy clusters and superclusters, which are the largest known structures in the universe. The formation of galaxies is closely linked to the processes of star formation and the dynamics of dark matter. In the early stages of galaxy formation, gas and dark matter clumped together under the influence of gravity, forming the first protogalaxies. These early galaxies were likely small and irregular in shape, but over time, they merged to form larger, more complex structures, such as the spiral and elliptical galaxies we observe today. The study of galaxy evolution involves understanding the processes that drive the formation of stars, the growth of supermassive black holes, and the interactions between galaxies. Observations of distant galaxies, which appear as they were billions of years ago due to the finite speed of light, provide a window into the early stages of galaxy formation and the evolution of cosmic structures over time. The role of black holes in cosmic evolution. The formation of stars and galaxies is also closely linked to the processes of nuclear fusion and supernova explosions. In the cores of stars, hydrogen atoms fuse to form helium, releasing energy that powers the star and creates heavier elements. When massive stars exhaust their nuclear fuel, they explode as supernovae, scattering these elements into space and creating the building blocks for new stars and planets. Supermassive black holes, which reside at the centers of most galaxies, are believed to play a crucial role in the formation and growth of galaxies. These black holes can influence the formation of stars and the distribution of matter within their host galaxies through their powerful gravitational pull and the energy released as matter falls into them. The study of these enigmatic objects is essential for understanding the dynamics and evolution of the cosmos. The search for life in the universe. One of the most profound questions that the universe poses is whether we are alone in it. The search for extraterrestrial life has been a driving force in astronomy and planetary science, leading to the discovery of thousands of exoplanets, planets orbiting stars outside our solar system. Some of these exoplanets are located in the habitable zones of their stars, where conditions might be suitable for life as we know it. The discovery of exoplanets. The discovery of exoplanets has revolutionized our understanding of planetary systems and the potential for life beyond Earth. Since the first exoplanet was discovered in 1992, thousands more have been identified, with many located in the habitable zones of their parent stars. These discoveries have shown that planets are common throughout the universe and that planetary systems can be incredibly diverse. Exoplanets come in a wide range of sizes, compositions, and orbital configurations. Some are gas giants similar to Jupiter and Saturn, while others are rocky planets like Earth. The study of exoplanets involves understanding their atmospheres, climates, and potential for hosting life. The discovery of Earth-like exoplanets in the habitable zones of their stars has intensified the search for life beyond our solar system. The search for biosignatures and technosignatures. The search for life extends beyond just finding habitable planets. It also involves the search for biosignatures, chemical signs of life, in the atmospheres of exoplanets. Biosignatures might include gases like oxygen, methane, and water vapor, which could indicate the presence of biological processes similar to those on Earth. In addition to biosignatures, scientists are also searching for technosignatures, indicators of advanced civilizations, such as artificial light, industrial pollution, or large-scale engineering projects. Projects like SETI search for extraterrestrial intelligence continue to scan the skies for signals that could indicate the presence of alien civilizations, while new missions and telescopes are being designed to detect signs of life on distant worlds, the future of cosmic exploration. As we continue to explore the universe, we are entering a new era of discovery, driven by advancements in technology and the development of new observational tools. Space telescopes, such as the James Webb Space Telescope, are poised to revolutionize our understanding of the cosmos by allowing us to peer deeper into space and time than ever before. The next generation of space telescopes. The James Webb Space Telescope, JWST, launched in 2021, is the most advanced space observatory ever built. With its powerful infrared capabilities, JWST is able to observe the earliest galaxies, study the formation of stars and planets, and analyze the atmospheres of exoplanets in unprecedented detail. JWST's observations are expected to answer some of the most fundamental questions about the origins and evolution of the universe. In addition to JWST, other next-generation space telescopes are being planned, including the Extremely Large Telescope ELT and the Square Kilometre Array SKA. These instruments will offer unprecedented resolution and sensitivity, allowing us to study the formation of the first stars and galaxies, map the distribution of dark matter, and search for signs of life on distant exoplanets. The exploration of our solar system. The future of cosmic exploration also involves the continued exploration of our own solar system. Missions to Mars, such as the Perseverance rover, are searching for signs of past life and preparing for future human exploration. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, are also prime targets for exploration, as they are believed to harbor subsurface oceans that could provide the conditions necessary for life. The exploration of the outer planets and their moons, as well as missions to asteroids and comets, will provide valuable insights into the formation and evolution of our solar system. These missions will also help us understand the potential for life in other parts of the universe and the processes that have shaped our planetary neighborhood. The philosophical implications of cosmic discovery. The exploration of the universe is not just a scientific endeavor. It also has profound philosophical implications. The discoveries we make about the cosmos challenge our understanding of reality, our place in the universe, and the nature of existence itself. The questions posed by cosmology about the origins of the universe, the nature of time and space, and the possibility of life beyond Earth are deeply intertwined with the fundamental questions of philosophy, the nature of reality and existence. As we continue to explore the universe, we are forced to confront the limitations of our knowledge and the mysteries that remain unsolved. The vastness of the cosmos, with its countless galaxies, stars, and planets, reminds us of our smallness in the grand scheme of things, but it also inspires a sense of wonder and curiosity that drives us to seek answers to the most profound questions of existence. The discoveries we make in cosmology often challenge our most deeply held beliefs about the nature of reality. The concept of a multiverse, for example, raises questions about the nature of existence and the possibility of alternate realities with different physical laws. The idea that our universe might be just one of many suggests that the reality we experience is just one of many possible outcomes, each with its own set of circumstances and conditions. The exploration of the universe also challenges our understanding of time and space. The realization that time is not an absolute constant, but rather a variable that can be influenced by gravity and the curvature of space-time, forces us to rethink our perception of the flow of time and the nature of causality. The concept of time travel, while still speculative, is another example of how our understanding of the universe can lead to profound philosophical questions about the nature of reality and the possibility of alternate timelines and dimensions. The search for meaning in the cosmos. The exploration of the universe is also a search for meaning, an attempt to understand our place in the grand scheme of things. The discovery of exoplanets and the search for extraterrestrial life raise questions about the uniqueness of life on Earth and the possibility of other intelligent civilizations in the cosmos. The idea that we might not be alone in the universe has profound implications for our understanding of life, consciousness, and the potential for contact with other civilizations. The search for meaning in the cosmos also involves exploring the origins of the universe and the forces that have shaped its evolution. The study of the Big Bang, the formation of galaxies and stars, and the processes that have led to the emergence of life on Earth all contribute to our understanding of the nature of existence and the possibility of a deeper, underlying purpose to the universe. The universe as a reflection of human curiosity. Ultimately, the exploration of the universe is a reflection of our innate human curiosity, the desire to understand the world around us and our place within it. The universe, with all its mysteries and wonders, is a mirror that reflects our deepest questions about life, existence, and the nature of reality. It is a journey that will continue to inspire and challenge us for generations to come, as we seek to unravel the mysteries of the cosmos and discover the true nature of the universe. This expanded text delves deeper into the concepts presented in the original passage, exploring the complexity, dynamism, and philosophical implications of the universe. It covers additional topics such as the scale of the cosmos, the role of dark matter and dark energy, the evolution of cosmic structures, the search for extraterrestrial life, and the future of cosmic exploration. If there are specific areas you'd like to expand further or additional topics to explore, feel free to let me know. The dynamic nature of the universe. The universe is not a static backdrop, but a dynamic, evolving entity. From the moment of its birth in the Big Bang, it has been in a constant state of change, with galaxies forming, stars being born and dying, and entire regions of space expanding at an ever-increasing rate. This continuous transformation is driven by the interplay of fundamental forces, gravity, electromagnetism, and the nuclear forces that govern the behavior of matter and energy on both microscopic and cosmic scales. The forces that shape the cosmos. The dynamic nature of the universe is fundamentally influenced by four fundamental forces. 1. Gravity. The most familiar of the forces, gravity is the attractive force that pulls matter together. It is the force responsible for the formation of stars, galaxies, and larger cosmic structures. Gravity governs the orbits of planets around stars, stars around galactic centers, and galaxies within clusters. On the largest scales, gravity shapes the structure of the universe, pulling matter into dense regions that eventually form galaxies and clusters. 2. Electromagnetism. This force governs the interactions between charged particles, such as electrons and protons, and is responsible for the formation of atoms and molecules. Electromagnetic forces give rise to light, heat, and other forms of radiation, playing a crucial role in the chemistry and physics of the cosmos. The electromagnetic force is also responsible for the light that stars emit, allowing us to observe distant objects in the universe. 3. Strong nuclear force. The strong nuclear force binds protons and neutrons together in atomic nuclei, overcoming the repulsive electromagnetic force between positively charged protons. This force is responsible for the stability of atomic nuclei and the energy released in nuclear fusion, the process that powers stars. 4. Weak nuclear force. The weak nuclear force is responsible for radioactive decay and certain nuclear reactions. It plays a key role in the process of nucleosynthesis, where elements are formed within stars. The weak force is essential in processes such as the fusion of hydrogen into helium in stars, which releases the energy that sustains stellar life. The evolution of the universe. One of the most profound aspects of the universe's dynamism is its ongoing expansion. This phenomenon was discovered by Edwin Hubble in 1929 when he observed that galaxies are moving away from each other, with more distant galaxies receding faster than those closer to us. This relationship, known as Hubble's law, provided the first direct evidence that the universe is expanding. The discovery of the universe's expansion led to the development of the Big Bang theory, which posits that the universe began as a singularity, a point of infinite density and temperature, about 13.8 billion years ago. In the first fractions of a second after the Big Bang, the universe underwent a rapid expansion known as inflation, during which it grew exponentially in size. This period of inflation smoothed out the universe's initial conditions, leading to the uniformity we observe today. As the universe expanded, it also cooled, allowing the formation of subatomic particles, atoms, and eventually the first stars and galaxies. The cosmic microwave background radiation CMB, the afterglow of the Big Bang, provides a snapshot of the universe when it was just 380000 years old. The CMB is a relic of the early universe and offers critical insights into its age, composition, and large-scale structure. The role of dark energy in the universe's expansion. The expansion of the universe is not uniform. It is influenced by the distribution of matter and energy, as well as by the mysterious force known as dark energy. Dark energy is the force that is causing the expansion of the universe to accelerate. Its discovery in the late 1990s was a major surprise to the scientific community, as it was previously believed that the expansion would slow down over time due to the gravitational pull of matter. Dark energy is thought to make up about 70% of the total energy content of the universe. While its exact nature remains unknown, it is believed to be a property of space itself, exerting a repulsive force that counteracts gravity. This repulsive force is causing galaxies to move apart at an accelerating rate, leading to the observation that the universe is expanding faster today than it did in the past. The acceleration of the universe's expansion has profound implications for its future. One possible scenario is the **Big Freeze**, in which the universe continues to expand and cool indefinitely. In this scenario, galaxies will drift further apart. Stars will burn out, and the universe will become a cold, dark, and empty place, with all activity eventually ceasing. Another possible scenario is the **Big Rip**, where the acceleration of the expansion becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atomic structures. In this catastrophic end, the fabric of space-time itself would be torn apart, leading to the complete disintegration of the universe. A third scenario is the Big Crunch where the expansion of the universe eventually reverses, leading to a collapse back into a singularity. This would be the opposite of the Big Bang, resulting in a cyclic model where the universe could potentially undergo endless cycles of expansion and contraction. The formation and death of stars and galaxies. The dynamic nature of the universe is also evident in the life cycles of stars and galaxies. Stars are born in clouds of gas and dust, known as nebulae, where gravity causes the material to collapse and form protostars. As these protostars grow, they heat up, eventually igniting nuclear fusion in their cores. This process converts hydrogen into helium, releasing energy that causes the star to shine. Stars spend most of their lives in a stable phase known as the main sequence, during which they fuse hydrogen into helium. The length of a star's main sequence phase depends on its mass. Massive stars burn through their fuel quickly, while smaller stars like the Sun can remain in this phase for billions of years. As stars exhaust their nuclear fuel, they undergo dramatic changes. Low-mass stars expand into red giants before shedding their outer layers and leaving behind a dense core known as a white dwarf. Massive stars, on the other hand, may end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. Galaxies, too, are dynamic entities, constantly evolving over billions of years. Galaxies can merge, forming larger and more complex structures. These galactic mergers can trigger bursts of star formation and lead to the growth of supermassive black holes at the centers of galaxies. The dynamic processes within galaxies, such as the formation of stars and the interaction of gravitational forces, contribute to the ongoing evolution of the cosmos. The study of these processes provides valuable insights into the history of the universe and the mechanisms that drive its evolution. The ongoing evolution of the universe. The universe's dynamic nature means that it is constantly changing, with new structures forming and old ones evolving or dissipating. This ongoing evolution is driven by the interplay of the fundamental forces and the properties of matter and energy. The large-scale structure of the universe, including galaxy clusters, superclusters, and the cosmic web, continues to evolve as galaxies move, merge, and interact. One of the most fascinating aspects of the universe's evolution is the formation of large-scale structures, such as the cosmic web, a vast network of dark matter and galaxies that stretches across the universe. The cosmic web is the result of billions of years of cosmic evolution, shaped by the force of gravity acting on the initial fluctuations in the density of matter that emerged from the Big Bang. The study of the cosmic web and the large-scale structure of the universe is essential for understanding the overall dynamics of the cosmos. It provides insights into the distribution of dark matter, the influence of dark energy, and the processes that drive the formation and evolution of galaxies. Conclusion. The dynamic nature of the universe is a testament to the complexity and beauty of the cosmos. From the smallest particles to the largest cosmic structures, the universe is in a constant state of change, driven by the interplay of fundamental forces and the properties of matter and energy. The ongoing expansion of the universe, influenced by dark energy, presents profound questions about the future of the cosmos and our place within it. As we continue to explore the universe and study its dynamic processes, we gain a deeper understanding of the forces that shape our existence and the ultimate fate of the cosmos. The mysteries of the universe's dynamism are far from being fully understood, but each new discovery brings us closer to unraveling the intricate web of interactions that govern the evolution of the universe. The multi-layered complexity of the cosmos. The universe is a tapestry woven from countless layers of complexity, extending from the tiniest subatomic particles to the largest structures in existence, galactic superclusters. This intricate structure reflects the interplay of fundamental forces, each governing different aspects of reality at various scales. Understanding these layers requires an exploration of the quantum realm, the domain of classical physics, and the vast cosmic structures that form the architecture of the universe. The quantum realm, the foundation of reality. At the smallest scales, the universe operates according to the principles of quantum mechanics, a branch of physics that describes the behavior of particles at the atomic and subatomic levels. In this realm, particles such as electrons, protons, and neutrons behave in ways that defy classical intuition. For instance, particles can exist in multiple states simultaneously, a phenomenon known as superposition. This means that a particle can be in more than one place at the same time or can possess multiple energies simultaneously. Another cornerstone of quantum mechanics is the concept of entanglement. When two particles become entangled, their states become linked, so that the state of one particle instantly influences the state of the other, regardless of the distance separating them. This spooky action at a distance, as Albert Einstein famously called it, has been experimentally confirmed and is one of the most mysterious aspects of quantum theory. The behavior of particles in the quantum realm is governed by probabilities rather than certainties. For example, the exact position or momentum of a particle cannot be precisely determined. Instead, quantum mechanics provides a probability distribution that describes the likelihood of finding a particle in a particular state. This inherent uncertainty is encapsulated in the Heisenberg uncertainty principle, which states that certain pairs of physical properties like position and momentum cannot both be known to arbitrary precision at the same time. Quantum mechanics is not just a theoretical construct, it has practical implications that permeate our everyday lives. Technologies such as semiconductors, lasers, and MRI machines all rely on quantum principles. Moreover, the quantum realm is the foundation of all matter and energy, giving rise to the particles and forces that shape the macroscopic world we experience. The classical realm, the laws of motion and gravity. At larger scales, the behavior of matter and energy is governed by the laws of classical physics. Isaac Newton's laws of motion describe how objects move and interact under the influence of forces, providing a framework for understanding the dynamics of everything from falling apples to orbiting planets. However, the true nature of gravity, the force that governs the motion of planets, stars, and galaxies, was revolutionized by Albert Einstein's theory of general relativity. General relativity describes gravity not as a force in the traditional sense, but as the curvature of space-time caused by the presence of mass and energy. Massive objects, such as stars and planets, warp the fabric of space-time, creating curves that other objects follow, which we perceive as the force of gravity. One of the most striking predictions of general relativity is the existence of black holes, regions of space where gravity is so strong that not even light can escape. Black holes are formed when massive stars collapse under their own gravity, compressing all their mass into a singularity, a point of infinite density where the known laws of physics break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing can return. General relativity also predicts the bending of light by gravity, known as gravitational lensing. This effect has been observed in numerous astronomical settings where the light from distant stars and galaxies is bent around massive objects like galaxy clusters, allowing us to see these objects magnified and distorted. Gravitational lensing is a powerful tool in modern astrophysics, enabling the study of dark matter, the distribution of galaxies, and the expansion of the universe. The unresolved mystery, quantum gravity. While quantum mechanics and general relativity have been remarkably successful in their respective domains, they are fundamentally incompatible when applied together, particularly in extreme environments such as black holes or the early universe. This incompatibility arises because quantum mechanics governs the behavior of particles on the smallest scales, where the effects of gravity are negligible, while general relativity describes the large-scale structure of space-time, where quantum effects are usually insignificant. The quest to reconcile these two pillars of modern physics has led to the search for a theory of quantum gravity, a framework that would unify quantum mechanics and general relativity into a single, coherent theory. Such a theory would provide a deeper understanding of the fundamental nature of reality, explaining phenomena that are currently beyond the reach of either quantum mechanics or general relativity alone. Several approaches to quantum gravity have been proposed, including string theory and loop quantum gravity. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but one-dimensional strings that vibrate at different frequencies. These vibrations give rise to the various particles and forces observed in nature. String theory also predicts the existence of additional dimensions beyond the familiar three spatial dimensions and one time dimension. Loop quantum gravity, on the other hand, attempts to quantize space-time itself, proposing that space-time is composed of discrete loops rather than being a smooth continuum. This approach suggests that space and time have a granular structure at the smallest scales, which could lead to a better understanding of the quantum nature of black holes and the early universe. Despite significant progress, a complete and experimentally verified theory of quantum gravity remains elusive. The resolution of this mystery would represent a major breakthrough in our understanding of the universe, potentially revealing new insights into the nature of space, time, and the fundamental forces that govern the cosmos. The cosmic structures, stars, planets, and galaxies. Beyond the quantum and classical realms lies the complexity of astrophysical objects and structures. Stars, planets, and galaxies are formed through processes that involve the interplay of gravity, nuclear fusion, and electromagnetic forces. These objects are the building blocks of the visible universe, each contributing to the grand cosmic tapestry in its own way. Stars are the fundamental units of astrophysical structures. They are born in clouds of gas and dust known as nebulae, where gravitational forces cause the material to collapse and form protostars. As a protostar grows in mass, it heats up and eventually ignites nuclear fusion in its core, converting hydrogen into helium and releasing energy in the process. This energy radiates outward, causing the star to shine and creating the pressure needed to counteract the inward pull of gravity. Stars vary greatly in size, temperature, and brightness, ranging from small, cool red dwarfs to massive, hot blue giants. The life cycle of a star is determined by its mass, with more massive stars burning through their nuclear fuel quickly and ending their lives in spectacular supernova explosions. These explosions scatter heavy elements into space, enriching the interstellar medium and providing the material for the formation of new stars and planets. Planets form from the leftover material surrounding a young star. This material, known as a protoplanetary disk, gradually coalesces into larger and larger bodies through the process of accretion. Over millions of years, these bodies are other objects that orbit the star. The diversity of planetary systems observed in the universe is astonishing, with planets ranging from rocky Earth-like worlds to gas giants like Jupiter and Saturn. The study of planets and their formation provides critical insights into the conditions necessary for life to emerge. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary systems and raised the tantalizing possibility that life could exist elsewhere in the universe. Galaxies are massive systems composed of stars, gas, dust, and dark matter, all bound together by gravity. Galaxies are the fundamental units of the large-scale structure of the universe, and they come in a variety of shapes and sizes, including spiral, elliptical, and irregular forms. The Milky Way, our home galaxy, is a spiral galaxy with a central bulge surrounded by spiral arms filled with stars, gas, and dust. Galaxies are not isolated objects. They interact with one another through gravitational forces, leading to mergers and collisions that can dramatically alter their structure and trigger bursts of star formation. These interactions are a key driver of galactic evolution, shaping the appearance and composition of galaxies over billions of years. Galactic clusters and superclusters, Galaxies themselves are part of even larger structures known as galaxy clusters and superclusters. Galaxy clusters are collections of hundreds or thousands of galaxies bound together by gravity, often containing vast amounts of hot gas that emits X-rays. These clusters are the largest gravitationally bound structures in the universe and play a crucial role in understanding the distribution of dark matter and the dynamics of cosmic evolution. Superclusters are even larger assemblies of galaxy clusters, forming some of the most massive structures in the universe. These superclusters are part of the cosmic web, a vast network of filaments composed of dark matter and galaxies that spans the entire universe. The cosmic web is the large-scale structure of the universe, shaped by the gravitational pull of dark matter and the expansion of space. The cosmic web, the large-scale structure of the universe. The cosmic web is a vast network of interconnected filaments that form the large-scale structure of the universe. These filaments are composed primarily of dark matter, with galaxies and galaxy clusters embedded within them. The cosmic web is the result of billions of years of cosmic evolution, shaped by the force of gravity acting on the initial fluctuations in the density of matter that emerged from the Big Bang. The formation of the cosmic web began shortly after the Big Bang, when tiny fluctuations in the density of matter grew over time due to gravitational attraction. These fluctuations eventually led to the formation of the first stars and galaxies, which clustered together to form larger structures. As the universe continued to expand, these structures evolved into the filaments, clusters, and voids that make up the cosmic web. The study of the cosmic web is essential for understanding the overall dynamics of the universe. It provides insights into the distribution of dark matter, the influence of dark energy, and the processes that drive the formation and evolution of galaxies. Observations of the cosmic web also help to test theories of cosmology and the large-scale behavior of the universe. Conclusion. The multi-layered complexity of the cosmos reflects the intricate interplay of fundamental forces and the diversity of structures that make up the universe. From the quantum realm, where particles behave in ways that challenge our classical understanding, to the vast cosmic web that spans the universe, the layers of complexity in the cosmos are interconnected and interdependent. Understanding these layers requires an exploration of both the smallest scales, governed by quantum mechanics, and the largest structures, shaped by gravity and dark matter. The quest to reconcile quantum mechanics and general relativity through a theory of quantum gravity remains one of the greatest challenges in modern physics, with the potential to unlock new insights into the fundamental nature of reality. The study of astrophysical objects and structures, from stars and planets to galaxies and clusters, reveals the dynamic and evolving nature of the universe. These objects are the building blocks of the cosmos, each contributing to the grand tapestry of the universe in its own way. As we continue to explore the complexities of the cosmos, we gain a deeper understanding of the forces that shape our existence and the ultimate fate of the universe. The role of dark matter and dark energy. One of the most intriguing aspects of the universe is the existence of dark matter and dark energy, two components that together make up about 95% of the total mass energy content of the cosmos. Despite their prevalence, these components remain shrouded in mystery as they do not emit, absorb, or reflect light, making them invisible to direct observation. However, their effects are observable through their gravitational influence on visible matter and the large-scale structure of the universe, making them essential to our understanding of cosmic evolution. Dark matter, the invisible backbone of the universe. Dark matter constitutes approximately 27% of the universe's total mass energy content. Unlike ordinary matter, which interacts with electromagnetic forces and is therefore detectable through light, dark matter interacts primarily through gravity. This elusive substance does not emit, absorb, or reflect any form of electromagnetic radiation, making it invisible to telescopes that rely on light detection. Despite this, dark matter's presence is inferred from its gravitational effects on visible matter, radiation, and the structure of the universe. One of the primary pieces of evidence for dark matter comes from the observation of galaxy rotation curves. In a typical galaxy, the stars at the outer edges should orbit more slowly than those near the center, where most of the visible mass is concentrated. However, observations show that the outer stars orbit at nearly the same speed as those closer to the center. This unexpected result suggests the presence of an unseen mass distributed throughout the galaxy, providing the necessary gravitational pull to maintain these higher rotation speeds. Further evidence for dark matter is found in the gravitational lensing of light from distant galaxies. When light passes near a massive object, such as a galaxy cluster, it is bent by the gravitational field, creating a lensing effect. The degree of lensing observed often exceeds what would be expected based solely on the visible matter in the cluster, indicating the presence of additional unseen mass, dark matter. Dark matter also plays a crucial role in the formation of large-scale structures in the universe. In the early universe, dark matter provided the gravitational scaffolding around which ordinary matter could clump together, leading to the formation of galaxies, clusters, and superclusters. Without dark matter, these structures would not have formed as they did, and the universe would look vastly different. The nature of dark matter. Despite its significant influence on the cosmos, the nature of dark matter remains one of the most profound mysteries in modern physics. Several candidates have been proposed to explain dark matter, each with its own implications for particle physics and cosmology. 1. Weakly interacting massive particles. WIMPs, WIMPs are hypothetical particles that interact with ordinary matter only through the weak nuclear force and gravity, making them extremely difficult to detect. These particles are a leading candidate for dark matter because they would have been produced in large quantities during the early moments of the Big Bang, consistent with the amount of dark matter observed today. 2. Axions. Axions are another class of hypothetical particles much lighter than WIMPs that could account for dark matter. These particles were originally proposed to solve a problem in quantum chromodynamics (QCD), a theory that describes the strong nuclear force. Axions could also interact very weakly with photons, leading to various experimental efforts to detect them through their conversion into light under strong magnetic fields. 3. Sterile neutrinos. Sterile neutrinos are a type of neutrino that does not interact via the weak nuclear force, making them even harder to detect than regular neutrinos. If they exist, sterile neutrinos could contribute to the dark matter content of the universe, though their detection remains a significant challenge. 4. Primordial black holes. Another exotic possibility is that dark matter could consist of primordial black holes formed in the early universe. These black holes would be much smaller than those formed from collapsing stars and could potentially account for a portion of dark matter. However, this idea is less favored due to the difficulty in explaining all observed dark matter phenomena with black holes alone. Despite extensive experimental efforts, direct detection of dark matter particles has so far been unsuccessful. Experiments using deep underground detectors, particle accelerators like the Large Hadron Collider (LHC), and astronomical observations continue to search for signs of dark matter, but its true nature remains elusive. The resolution of this mystery could lead to groundbreaking discoveries in both cosmology and particle physics, potentially revealing new aspects of the universe's fundamental structure. Dark energy, the force driving cosmic acceleration. While dark matter influences the structure and formation of the universe, dark energy is responsible for its large-scale dynamics, particularly the accelerating expansion observed in the universe. Dark energy makes up about 68% of the universe's total mass energy content and was discovered in the late 1990s through observations of distant Type Ia supernovae. These supernovae, which serve as standard candles due to their consistent brightness, revealed that the universe's expansion rate is not slowing down as expected, but is instead accelerating. This acceleration was a shocking discovery, fundamentally altering our understanding of the cosmos. It implied that there is a repulsive force acting against gravity on cosmic scales, causing galaxies to move away from each other at an ever-increasing rate. This repulsive force is attributed to dark energy, though its exact nature remains one of the most significant unsolved problems in cosmology. Theories of dark energy. Several theories have been proposed to explain the nature of dark energy, each with different implications for the future of the universe. 1. Cosmological constant LAM. The simplest explanation for dark energy is that it is a property of space itself, represented by the cosmological constant lambda in Einstein's equations of general relativity. This constant energy density of empty space could provide the repulsive force needed to drive the universe's accelerated expansion. The cosmological constant is consistent with observations, but its small but non-zero value poses a significant puzzle known as the cosmological constant problem, which questions why the energy density of the vacuum is so much smaller than theoretical predictions. 2. Quintessence ***. Quintessence is a hypothetical dynamic field that could vary over time and space, unlike the constant energy density of the cosmological constant. This field would act like dark energy, driving the accelerated expansion of the universe. Quintessence models predict that the properties of dark energy could change over time, leading to different cosmic expansion rates in the past and future. 3. Modified gravity theories ***. Some theories suggest that dark energy might not be a substance or field, but rather an indication that our understanding of gravity is incomplete. Modified gravity theories propose changes to general relativity on large scales to account for the observed acceleration without invoking a new form of energy. These theories are still speculative and face challenges in fitting all observational data. 4. Phantom energy and the Big Rip ***. An extreme form of dark energy known as phantom energy could lead to a scenario where the universe's expansion rate increases so rapidly that it eventually tears apart galaxies, stars, planets, and even atomic structures in a catastrophic event known as the Big Rip. In this scenario, dark energy's density would increase over time, leading to an ever-accelerating expansion that ultimately destroys the fabric of space-time. The impact of dark matter and dark energy on the universe's fate. The interplay between dark matter and dark energy will ultimately determine the fate of the universe. If dark energy continues to dominate, the universe could continue expanding indefinitely, leading to a big freeze where galaxies drift apart, stars burn out, and the cosmos becomes a cold, dark, and empty place. In this scenario, the universe reaches a state of maximum entropy, with no sources of energy or heat to sustain any form of activity. Alternatively, if dark energy's properties change over time, the future of the universe could unfold in different ways. For example, a decrease in dark energy's influence could lead to a slowing expansion and a possible big crunch, where the universe eventually collapses back into a singularity. Conversely, an increase in dark energy could lead to the catastrophic Big Rip. The ongoing study of dark matter and dark energy is essential for understanding the universe's ultimate destiny. These mysterious components not only shape the structure and evolution of the cosmos, but also hold the key to answering some of the most profound questions about the nature of reality. Conclusion. Dark matter and dark energy are two of the most significant yet mysterious components of the universe. Together, they shape the cosmos on both small and large scales, influencing everything from the formation of galaxies to the expansion of space itself. While dark matter provides the gravitational scaffolding necessary for the creation of cosmic structures, dark energy drives the accelerated expansion that will determine the universe's fate. Despite the progress made in understanding these components, much remains unknown. The true nature of dark matter and dark energy continues to elude scientists, driving ongoing research and experimentation. The discovery of their origins and properties could revolutionize our understanding of the universe, offering new insights into the fundamental forces that govern reality and potentially leading to a unified theory of physics. As we continue to explore these cosmic mysteries, we move closer to uncovering the secrets of the universe and our place within it. The evolution of cosmic structures. The universe's complexity is not static. It has evolved over billions of years, giving rise to the intricate structures we observe today. The formation of galaxies, stars, and planets is the result of a long process of cosmic evolution that began with the Big Bang and continues to this day. This evolution is driven by fundamental forces, including gravity, electromagnetism, and nuclear interactions, which have shaped the cosmos from its earliest moments to its current state. The birth of the universe and the seeds of structure. In the moments immediately following the Big Bang, the universe was an incredibly hot and dense plasma, a nearly uniform soup of particles. As the universe expanded and cooled, the fundamental forces began to differentiate, and particles started to combine into atomic nuclei in a process known as nucleosynthesis. During this period, the universe was still largely homogeneous, with only tiny fluctuations in density present. These fluctuations were crucial, as they would later grow into the large-scale structures we see today. The first few 100,000 years after the Big Bang were dominated by radiation, with photons scattering off free electrons in the plasma, keeping the universe opaque. However, as the universe continued to expand and cool, it eventually reached a temperature where protons and electrons could combine to form neutral hydrogen atoms in a process called recombination. This allowed photons to travel freely, leading to the release of the cosmic microwave background CMB radiation, a faint glow that permeates the universe and provides a snapshot of the universe at that time. The tiny fluctuations in the density of matter observed in the CMB served as the seeds for the formation of all cosmic structures. These initial inhomogeneities, caused by quantum fluctuations during the inflationary period of the early universe, were magnified by the force of gravity, which began pulling matter into denser regions, leading to the formation of the first clumps of matter, the formation of the first stars and galaxies. As gravity continued to pull matter together, the first stars began to form about 100 million years after the Big Bang, marking the end of the cosmic dark ages, a period during which the universe had no luminous sources of light. These first stars, known as population 3 stars, were massive, hot, and short-lived. They were composed almost entirely of hydrogen and helium, the simplest and most abundant elements produced in the Big Bang nucleosynthesis. The fusion processes within these stars created heavier elements such as carbon, oxygen, and iron in their cores. The death of these first stars, often in violent supernova explosions, played a critical role in cosmic evolution. These explosions not only scattered heavy elements into the surrounding space, enriching the interstellar medium, but they also triggered the formation of new stars and provided the energy necessary to reionize the universe. Reionization is the process by which the neutral hydrogen in the early universe was ionized again, making the universe transparent to ultraviolet light and ending the cosmic dark ages. As these stars formed, they began to group together under the influence of gravity, creating the first protogalaxies. Over time, these protogalaxies merged and evolved into the larger galaxies we see today. The process of galaxy formation was complex and involved the interplay of dark matter, which provided the gravitational scaffolding, and baryonic matter, which cooled, condensed, and formed stars. The growth of galaxies and the formation of clusters galaxies did not evolve in isolation. They interacted with one another through gravitational forces, leading to collisions and mergers that significantly influenced their shapes, sizes, and compositions. When two galaxies collide, their stars typically pass by one another due to the vast distances between them, but the gas within the galaxies can collide, triggering new waves of star formation. These mergers often result in the formation of elliptical galaxies, particularly in environments where many mergers occur. Over billions of years, galaxies continue to grow and evolve, forming larger structures such as galaxy clusters and superclusters. Galaxy clusters are collections of hundreds or even thousands of galaxies bound together by gravity, often containing vast amounts of hot gas that emit X-rays. These clusters represent the largest gravitationally bound structures in the universe and are critical to understanding the distribution of dark matter and the dynamics of cosmic evolution. Superclusters are even larger structures, consisting of multiple galaxy clusters linked together by long filaments of dark matter and galaxies. These superclusters are part of the cosmic web, a vast network of interconnected filaments that form the large-scale structure of the universe. The cosmic web is the result of billions of years of cosmic evolution, shaped by the force of gravity acting on the initial fluctuations in the density of matter that emerged from the Big Bang. The role of supermassive black holes in galactic evolution. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole with masses ranging from millions to billions of times that of the Sun. These black holes are not merely passive objects. They play a crucial role in the formation and evolution of galaxies. The relationship between a galaxy and its central black hole is complex and reciprocal. While the black hole's growth is fueled by the accretion of matter from its host galaxy, the energy released during this process can influence the galaxy's evolution. As matter falls into a supermassive black hole, it forms an accretion disk, heating up and emitting vast amounts of energy, particularly in the form of X-rays. This process can produce powerful jets of particles that are ejected at nearly the speed of light, extending far beyond the host galaxy. These jets can impact the surrounding environment by heating the interstellar and intergalactic medium, potentially suppressing star formation by preventing the cooling of gas clouds necessary for new stars to form. This feedback mechanism, known as active galactic nucleus AGN feedback, is believed to regulate the growth of both the black hole and its host galaxy. The energy output from AGNs can drive galactic winds that expel gas from the galaxy, effectively quenching star formation and influencing the galaxy's evolution. AGN feedback is also thought to play a role in the formation of large-scale cosmic structures, as it can affect the distribution of gas in galaxy clusters. The formation of planetary systems. While galaxies and clusters represent the largest structures in the universe, the formation of planetary systems is a key aspect of cosmic evolution on smaller scales. Planetary systems, like our solar system, form within the dense regions of molecular clouds, vast cold clouds of gas and dust within galaxies. These regions collapse under their own gravity, forming protostars surrounded by rotating disks of gas and dust. Within these protoplanetary disks, particles of dust collide and stick together, gradually building up into larger bodies known as planetesimals. Over time, these planetesimals coalesce into planets, moons, and other objects that orbit the central star. The formation of planetary systems is a complex process influenced by various factors, including the star's mass, the composition of the disk, and the presence of nearby stars. The study of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary formation and revealed a staggering diversity of planetary systems. Some exoplanets are gas giants like Jupiter, orbiting close to their stars, while others are rocky Earth-like planets located in the habitable zones where liquid water could exist. These discoveries have profound implications for our understanding of the potential for life elsewhere in the universe. The cosmic web and the large-scale structure of the universe. The cosmic web is the large-scale structure of the universe, composed of filaments of dark matter and galaxies that stretch across vast distances. This structure is a product of billions of years of cosmic evolution, shaped by the force of gravity acting on the initial density fluctuations that emerged from the Big Bang. The cosmic web is not uniform. It contains dense regions where galaxies and galaxy clusters are concentrated, as well as vast voids with very few galaxies. The formation of the cosmic web began with the growth of small initial fluctuations in the density of matter. Over time, gravity amplified these fluctuations, causing matter to clump together and form the first stars and galaxies. These galaxies then merged to form larger structures, such as galaxy clusters and superclusters, which are connected by long filaments of dark matter and galaxies. The study of the cosmic web provides valuable insights into the overall dynamics of the universe. It helps scientists understand the distribution of dark matter, the influence of dark energy, and the processes that drive the formation and evolution of galaxies. Observations of the cosmic web also provide a means of testing theories of cosmology and the large-scale behavior of the universe. Conclusion. The evolution of cosmic structures is a testament to the dynamic and interconnected nature of the universe. From the formation of the first stars and galaxies to the growth of galaxy clusters and the cosmic web, the universe has undergone a complex process of development over billions of years. This process is driven by the fundamental forces of nature, including gravity, electromagnetism, and nuclear interactions, which have shaped the cosmos from its earliest moments to the present day. The study of cosmic evolution provides critical insights into the forces and processes that have shaped the universe and continues to drive the quest to understand the cosmos' fundamental nature. As we explore the evolution of stars, galaxies, black holes, and planetary systems, we gain a deeper appreciation for the complexity and beauty of the universe and our place within it. The ongoing study of cosmic evolution will undoubtedly reveal even more about the intricate web of interactions that govern the cosmos, bringing us closer to understanding the ultimate fate of the universe. The search for life in the universe. One of the most profound and enduring questions that the universe poses is whether we are alone in it. The search for extraterrestrial life has been a driving force in astronomy, planetary science, and even philosophy, as it touches on fundamental questions about the nature of life, our place in the cosmos, and the potential for other civilizations beyond Earth. The discovery of life beyond our planet would not only revolutionize our understanding of biology and evolution, but also challenge our assumptions about the uniqueness of life on Earth. The discovery of exoplanets and the search for habitable worlds. The search for life beyond Earth has been significantly advanced by the discovery of exoplanets, planets that orbit stars outside our solar system. Since the first exoplanet was discovered in 1992, thousands more have been identified thanks to advances in observational technology and methods. These discoveries have revealed that planetary systems are common throughout the galaxy, with many stars hosting multiple planets. A key focus of exoplanet research is the identification of planets located in the habitable zone of their parent stars. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on the planet's surface, a critical factor for life as we know it. Planets within this zone are prime candidates in the search for life, as liquid water is essential for the biochemical processes that sustain living organisms. The diversity of exoplanets discovered has been astounding. They range from gas giants many times the size of Jupiter to rocky, Earth-like planets. Some exoplanets orbit their stars in just a few days, while others have orbits that take hundreds of Earth years to complete. The discovery of exoplanets in the habitable zones of stars has raised the tantalizing possibility that some of these worlds could host life, or at least the conditions necessary for life to arise. Biosignatures, the chemical signs of life. The search for life on exoplanets extends beyond simply finding habitable worlds. It also involves the detection of biosignatures, chemical signs that may indicate the presence of life. Biosignatures are specific molecules or patterns in a planet's atmosphere or surface that could be produced by biological processes. One of the most well-known biosignatures is oxygen, which on Earth is primarily produced by photosynthetic organisms. The presence of large amounts of oxygen in an exoplanet's atmosphere could suggest the existence of similar life forms. However, it's important to note that oxygen can also be produced by non-biological processes, so its presence alone is not definitive proof of life. Other potential biosignatures include methane, which on Earth is produced by both biological and geological processes, and water vapor, which is essential for life as we know it. The detection of a combination of these gases, especially in ratios that are out of equilibrium, could strengthen the case for the presence of life. The study of exoplanet atmospheres has become a critical area of research in the search for biosignatures. Instruments like the James Webb Space Telescope JWST are equipped with advanced spectrometers capable of analyzing the light passing through or reflecting off a planet's atmosphere. By studying the absorption lines in the spectrum, scientists can determine the composition of the atmosphere and search for signs of life. The search for life within our solar system. While the search for life on exoplanets has garnered much attention, scientists are also exploring the possibility of life within our own solar system. Several bodies within the solar system are considered potential candidates for harboring life, particularly microbial life, which could exist in environments very different from those on Earth. Mars. Has been a primary focus of the search for extraterrestrial life for decades. The red planet has a history of water, with evidence of ancient rivers, lakes, and possibly even oceans. While Mars' surface today is cold and dry, with a thin atmosphere that offers little protection from solar radiation, subsurface environments might still be hospitable to microbial life. The discovery of seasonal methane emissions on Mars has sparked interest, as methane can be produced by biological activity, although geological processes are also possible sources. Robotic missions such as NASA's Perseverance rover are currently exploring Mars' surface, searching for signs of past life in ancient lakebeds and examining rock samples that could contain fossilized microorganisms. Future missions may focus on drilling into the subsurface to search for liquid water and potential habitats for life. Europa***, one of Jupiter's moons, is another prime candidate in the search for extraterrestrial life. Beneath its icy surface, Europa is believed to harbor a subsurface ocean of liquid water, kept warm by tidal forces generated by Jupiter's strong gravitational pull. This ocean could provide the necessary conditions for life, including chemical nutrients and energy sources from hydrothermal vents on the ocean floor, similar to those that support life in Earth's deep oceans. NASA's upcoming Europa Clipper mission, scheduled for launch in the 2020s, aims to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, searching for biosignatures and assessing the moon's habitability. Enceladus***, a moon of Saturn, is another intriguing target in the search for life. Like Europa, Enceladus has a subsurface ocean beneath its icy crust. Geysers on Enceladus' surface eject plumes of water vapor, ice particles, and organic molecules into space, providing direct access to material from the moon's interior. The presence of complex organic compounds in these plumes, detected by the Cassini spacecraft, suggests that Enceladus could have the ingredients necessary for life. The study of these plumes offers a unique opportunity to search for signs of life without needing to drill through the moon's ice. Future missions could focus on capturing and analyzing plume material in more detail to search for biomarkers or even microbial life. Titan***, Saturn's largest moon, presents a very different but equally intriguing environment for the search for life. Titan has a thick atmosphere rich in organic molecules and surface lakes and rivers composed of liquid methane and ethane. While the extremely cold temperatures on Titan's surface make water-based life unlikely, the abundance of organic molecules raises the possibility of life forms based on different biochemistry. NASA's Dragonfly mission, planned for the mid-2020s, will send a rotorcraft to explore Titan's surface, investigating its chemistry and searching for signs of prebiotic processes that could lead to the development of life. The Fermi paradox and the search for intelligent life. While the search for microbial life is a major focus, the possibility of intelligent extraterrestrial civilizations has also captured the imagination of scientists and the public alike. The Fermi paradox, named after physicist Enrico Fermi, highlights the apparent contradiction between the high probability of extraterrestrial civilizations in the galaxy and the lack of evidence for or contact with such civilizations. Several explanations have been proposed for the Fermi paradox, ranging from the idea that intelligent civilizations are extremely rare or short-lived, to the possibility that they are avoiding contact with us or that we are simply not looking in the right way. The search for extraterrestrial intelligence SETI has been ongoing for decades, using radio telescopes to listen for signals that might be evidence of intelligent civilizations. While no definitive signals have been detected, the search continues, with new strategies and technologies being developed to improve our chances of detecting extraterrestrial intelligence. One intriguing possibility is the detection of technosignatures, indicators of advanced technology, such as artificial light, industrial pollution, or large-scale engineering projects. These signatures could potentially be detected through astronomical observations, offering an alternative to traditional radio searches. The philosophical implications of finding life beyond Earth. The discovery of even the simplest forms of life beyond Earth would have profound implications for our understanding of biology, evolution, and the uniqueness of life on our planet. It would suggest that life is not a rare or unique occurrence, but a common outcome of the right conditions in the universe. This would prompt a re-evaluation of our place in the cosmos, potentially altering our perspectives on everything from the development of life to the evolution of intelligence and consciousness. The discovery of intelligent extraterrestrial civilizations would raise even more profound questions about communication, coexistence, and the potential for collaboration or conflict. It could lead to new philosophical and ethical considerations about how we interact with other intelligent beings and the role humanity plays in the broader context of the universe. Conclusion. The search for life in the universe is one of the most exciting and profound scientific endeavors of our time. From the exploration of exoplanets in the habitable zones of distant stars, to the study of potentially life-supporting environments within our own solar system, this quest drives advances in technology, deepens our understanding of biology and chemistry, and expands our horizons about what is possible in the cosmos. While the search has yet to yield definitive evidence of extraterrestrial life, each discovery brings us closer to answering the age-old question of whether we are alone in the universe. As we continue to explore the cosmos, the possibility of finding life beyond Earth remains one of the most compelling motivations for scientific inquiry, promising to reshape our understanding of the universe and our place within it. The future of cosmic exploration. As we continue to explore the universe, we stand on the cusp of a new era of discovery, one that is increasingly driven by rapid advancements in technology and the development of powerful new observational tools. The future of cosmic exploration promises to reveal unprecedented details about the cosmos, from the farthest reaches of space and time to the most intricate processes occurring within our own solar system. The next generation of space telescopes. One of the most significant developments in cosmic exploration is the deployment of the James Webb Space Telescope JWST**, which represents a major leap forward in our ability to observe the universe. JWST is designed to observe the cosmos in infrared wavelengths, allowing it to peer through clouds of dust and gas that obscure visible light. This capability is crucial for studying the formation of stars and planets, as well as observing the early universe, just a few 100 million years after the Big Bang. JWST's powerful instruments will enable astronomers to study the atmospheres of exoplanets in greater detail than ever before, searching for signs of habitability and potential biosignatures. By analyzing the light passing through an exoplanet's atmosphere as it transits its host star, JWST can detect the presence of key molecules such as water vapor, methane, and oxygen, which could indicate the presence of life. Following JWST, other ambitious space telescopes are planned, each designed to address specific questions about the universe. For example, the Nancy Grace Roman Space Telescope **, formerly known as WF1, is set to launch in the mid-2020s and will focus on investigating dark energy, exoplanets, and the structure of the universe. It will have a wide field of view, allowing it to survey vast areas of the sky and conduct deep imaging of large cosmic structures. Another proposed mission, **Louvois, Large UV/optical/IR Surveyor **, aims to be a multi-wavelength observatory capable of imaging exoplanets directly and studying their atmospheres in detail. Louvois would be able to resolve Earth-like planets around nearby stars, providing the most detailed search for signs of life beyond our solar system. These telescopes, along with ground-based observatories like the *** Extremely Large Telescope (ELT), ***, and the *** Square Kilometer Array, SKA***, will work in concert to push the boundaries of what we know about the universe, providing new insights into the formation of galaxies, the nature of dark matter and dark energy, and the potential for life elsewhere in the cosmos. The exploration of the solar system. While space telescopes look outward to distant stars and galaxies, the exploration of our own solar system continues to be a major focus of cosmic exploration. The search for life, the study of planetary processes, and the desire to understand the history of our celestial neighborhood drive a diverse array of missions. *** Mars. remains a prime target for exploration, with multiple missions planned to study its geology, climate, and potential for past or present life. NASA's Perseverance rover is currently exploring the Jezero crater, searching for signs of ancient microbial life and collecting samples that will be returned to Earth by future missions. These samples could provide definitive evidence of whether life ever existed on Mars. The Artemis program aims to return humans to the Moon by the mid-2020s, with the goal of establishing a sustainable human presence on the lunar surface. The program will serve as a stepping stone for future missions to Mars and beyond, providing valuable experience in living and working on other celestial bodies. The Moon's south pole, with its permanently shadowed regions that may contain water ice, is of particular interest as a potential resource for future exploration. Europa Clipper set to launch in the 2020s, will conduct detailed reconnaissance of Jupiter's moon Europa, which is believed to harbor a subsurface ocean beneath its icy crust. The mission will search for signs of habitability and gather data on the moon's ice shell and subsurface ocean, offering insights into whether Europa could support life. Dragonfly a mission to Saturn's moon Titan, will launch in the mid-2020s and explore Titan's surface with a rotorcraft. Titan is unique in the solar system, with a thick atmosphere and lakes of liquid methane and ethane. Dragonfly will study the moon's chemistry and search for prebiotic processes that could lead to the formation of life. Sample return missions. Are also a focus of future exploration. For example, NASA's OSIRIS-REx mission is returning samples from the asteroid Bennu, which could provide clues about the early solar system and the building blocks of life. Similarly, Japan's Hayabusa 2 mission successfully returned samples from the asteroid Ryugu, offering insights into the composition and history of these primitive bodies. The search for life beyond Earth. The search for life beyond Earth remains one of the most compelling goals of cosmic exploration. As technology advances, our ability to detect and study potential biosignatures on distant worlds improves, bringing us closer to answering the question of whether we are alone in the universe. The discovery of exoplanets in the habitable zones of their stars has intensified the search for life. Instruments like JWST and future telescopes will analyze the atmospheres of these planets, searching for signs of habitability and potential life. The discovery of even simple microbial life would have profound implications for our understanding of biology and the prevalence of life in the universe. In our own solar system, missions to Mars, Europa, Enceladus, and Titan are designed to search for signs of life or conditions that could support life. The discovery of life on any of these worlds would revolutionize our understanding of biology and the potential for life to exist in diverse environments. Human exploration and the future of space travel. Human exploration of space is poised to enter a new phase, with ambitious plans to return to the Moon, explore Mars, and even venture to the outer planets. The Artemis program aims to land humans on the Moon by the mid-2020s and establish a sustainable presence, serving as a stepping stone for future missions to Mars. Mars is the next major target for human exploration, with NASA and private companies like SpaceX planning missions to send humans to the Red Planet in the coming decades. These missions will require advances in space travel, life support, and habitat technologies, as well as the development of new strategies for living and working on a planet with a hostile environment. Beyond Mars, the outer planets and their moons present intriguing targets for future human exploration. Missions to these distant worlds will require advances in propulsion technology, radiation protection, and long-duration spaceflight. The challenges are significant, but the potential rewards, new discoveries about the origins of the solar system, the search for life, and the expansion of human presence beyond Earth, are enormous. The philosophical implications of cosmic discovery. The exploration of the universe is not just a scientific endeavor, it also has profound philosophical implications. Each discovery we make about the cosmos challenges our understanding of reality, our place in the universe, and the nature of existence itself. As we discover more about the origins of the universe, the formation of galaxies, and the potential for life elsewhere, we are forced to confront fundamental questions about our existence. Are we alone in the universe, or is life a common outcome of the right conditions? What does the vastness of the cosmos say about the significance of human life? How do we reconcile our understanding of the physical universe with our philosophical and spiritual beliefs? The exploration of the cosmos also raises ethical questions. As we expand our presence in space, how do we ensure that our activities do not harm other worlds or potential life forms? What responsibilities do we have to protect and preserve the environments we explore? These questions will become increasingly important as human exploration of space progresses. The future of cosmic exploration, a journey without end. The future of cosmic exploration is a journey without end, driven by our innate curiosity and desire to understand the universe. Each new discovery opens the door to new questions, new challenges, and new possibilities. As we push the boundaries of human knowledge, we will continue to reveal the mysteries of the cosmos, challenging our understanding of reality and inspiring future generations to explore the final frontier. The exploration of the universe is a testament to the ingenuity and determination of humanity. It is a journey that has the potential to transform our understanding of the cosmos and our place within it, offering insights that could shape the future of science, philosophy, and our collective consciousness. As we look to the stars, we are reminded that the journey of exploration is not just about discovering new worlds. It is also about discovering ourselves and our potential as a species. The universe as a reflection of human curiosity. The exploration of the universe is, at its core, a profound expression of human curiosity, an innate drive that has propelled our species from the early days of stargazing to the sophisticated scientific endeavors of today. This curiosity is more than just a desire to collect facts or map the stars. It is a fundamental aspect of our nature, pushing us to seek understanding, meaning, and connection with the cosmos. The universe, with its vastness and mystery, acts as a mirror, reflecting back to us the deepest questions we hold about life, existence, and the nature of reality. The scale of the cosmos, a source of awe and wonder. The sheer scale of the universe is both humbling and awe-inspiring. When we consider the vast distances between stars, the immense size of galaxies, and the incomprehensible number of celestial bodies, we are reminded of our smallness in the grand scheme of things. The observable universe, spanning over 93 billion light-years, contains more stars than there are grains of sand on all the beaches of Earth, a fact that stretches the limits of human imagination. This scale prompts questions that are both scientific and philosophical. How did the universe come to be? What forces govern its vast expanse? What is our place within it? These questions are not new. They have been asked by humans for millennia, and they continue to drive our exploration of the cosmos. The desire to understand the scale of the universe has led to some of humanity's greatest achievements in science and technology. From the development of the telescope to the launch of space observatories like the Hubble Space Telescope, each step forward has expanded our view of the cosmos and deepened our understanding of its structure. As our tools have improved, so too has our ability to explore the universe, revealing its complexity and beauty in ever greater detail. The role of dark matter and dark energy, the hidden forces of the cosmos. As we delve deeper into the mysteries of the universe, we encounter phenomena that challenge our understanding of physics and the nature of reality itself. Dark matter and dark energy are two such mysteries, representing some of the most significant unknowns in modern cosmology. Together, they make up about 95% of the universe's total mass energy content, yet they remain largely invisible and elusive to direct observation. Dark matter is thought to act as the scaffolding of the universe, holding galaxies together and influencing their rotation rates. Without dark matter, the observed behavior of galaxies would be inexplicable, as the visible matter alone is insufficient to account for the gravitational forces at play. The existence of dark matter suggests that our understanding of the universe is incomplete, that there is much more to the cosmos than what we can see. Asterisk, asterisk. Dark energy, asterisk, asterisk, on the other hand, is the mysterious force driving the accelerated expansion of the universe. Its discovery in the late 1990s was a watershed moment in cosmology, revealing that the universe is not just expanding, but doing so at an increasing rate. This acceleration raises profound questions about the fate of the universe and the underlying nature of space-time. The study of dark matter and dark energy reflects our curiosity about the hidden aspects of reality, those forces and components that shape the universe but elude direct detection. They remind us that the universe is far more complex and mysterious than our senses can perceive, and they drive us to develop new theories, experiments, and technologies to uncover their nature. The evolution of cosmic structures, a story of creation and change. The universe is not a static entity. It is a dynamic, evolving system that has undergone profound changes over billions of years. The formation of galaxies, stars, and planets is a process that continues to this day, driven by the fundamental forces of nature. Understanding this evolution allows us to piece together the history of the cosmos and our place within it. In the beginning, the universe was a hot, dense soup of particles with no distinct structures. Over time, tiny fluctuations in the density of this primordial soup grew under the influence of gravity, leading to the formation of the first stars and galaxies. These early structures were the building blocks of everything we see today, from galaxy clusters to planetary systems. The evolution of cosmic structures is a testament to the power of natural processes to create complexity from simplicity. It reflects the delicate balance between the forces of nature, gravity, electromagnetism, and nuclear interactions that shape the cosmos. As we study these processes, we gain insight into the fundamental laws that govern the universe and the mechanisms that drive its ongoing evolution. This story of cosmic evolution is not just a scientific narrative. It is also a reflection of our search for meaning. The processes that gave rise to stars, planets, and life itself are part of a larger story that connects us to the cosmos. By understanding this story, we gain a deeper appreciation for the interconnectedness of all things and our place in the grand tapestry of the universe. The search for extraterrestrial life, a quest for connection. The search for life beyond Earth is one of the most compelling and profound aspects of cosmic exploration. It is a quest that goes beyond the scientific. It is driven by a deep-seated curiosity about whether we are alone in the universe and what other forms of life might exist. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up new possibilities for finding life elsewhere in the cosmos. As we identify planets in the habitable zones of their stars, where conditions might be right for life, we inch closer to answering the age-old question of whether life exists beyond Earth. The search for biosignatures, chemical signs of life, in the atmospheres of these exoplanets is a key focus of this quest. The detection of such signatures would have profound implications for our understanding of biology, evolution, and the uniqueness of life on Earth. It would suggest that life is not a rare occurrence but a common outcome in the universe, given the right conditions. The search for extraterrestrial life is also a search for connection. It reflects our desire to understand our place in the cosmos and to connect with other forms of life if they exist. The discovery of even the simplest life forms beyond Earth would challenge our assumptions about life and force us to reconsider our understanding of biology and the potential for life to thrive in diverse environments. The future of cosmic exploration, a journey of discovery. As we continue to explore the universe, we are entering a new era of discovery. Advances in technology, such as the development of new space telescopes and missions to other planets and moons, are pushing the boundaries of what we know about the cosmos. Each new discovery opens up new questions, challenges our understanding, and inspires further exploration. The *** James Webb Space Telescope, JWST***, with its ability to peer deeper into space and time than ever before, represents the cutting edge of this exploration. It will allow us to study the earliest galaxies, the formation of stars and planets, and the atmospheres of exoplanets in unprecedented detail. JWST, along with future missions like *** Europa, Clipper ***, and **** Dragonfly ***, will expand our knowledge of the solar system and the potential for life beyond Earth. Human exploration of space is also set to advance, with plans to return to the Moon, explore Mars, and venture further into the outer reaches of the solar system. These missions will require new technologies and strategies, as well as a deep commitment to the long-term exploration of the cosmos. The future of cosmic exploration is a journey that will continue to inspire and challenge us. It is a journey that reflects our innate human curiosity and our desire to understand the world around us. As we push the boundaries of knowledge, we are reminded that the universe is not just a collection of stars and galaxies. It is a mirror that reflects our deepest questions about life, existence, and the nature of reality. The philosophical implications of cosmic exploration. The exploration of the universe is not just a scientific endeavor, it is also a deeply philosophical one. The discoveries we make about the cosmos challenge our understanding of reality, our place in the universe, and the nature of existence itself. As we uncover the mysteries of the cosmos, we are forced to confront the limitations of our knowledge and the mysteries that remain unsolved. The vastness of the cosmos, with its countless galaxies, stars, and planets, reminds us of our smallness in the grand scheme of things. Yet, it also inspires a sense of wonder and curiosity that drives us to seek answers to the most profound questions of existence. The search for extraterrestrial life, the study of cosmic structures, and the exploration of dark matter and dark energy all reflect our desire to understand the fundamental nature of reality and our place within it. As we continue to explore the universe, we are challenged to rethink our assumptions, question our beliefs, and expand our understanding of what is possible. The discoveries we make may change the way we view the world, our place in it, and the nature of reality itself. The exploration of the universe is a journey that will continue to inspire and challenge us for generations to come. Conclusion. Ultimately, the exploration of the universe is a reflection of our innate human curiosity, the desire to understand the world around us and our place within it. The universe, with all its mysteries and wonders, is a mirror that reflects our deepest questions about life, existence, and the nature of reality. It is a journey that will continue to inspire and challenge us as we seek to unravel the mysteries of the cosmos and discover the true nature of the universe. This expanded exploration delves deeper into the concepts presented in the original passage, highlighting the complexity, dynamism, and philosophical implications of the universe. It touches on the scale of the cosmos, the hidden forces of dark matter and dark energy, the evolution of cosmic structures, the search for extraterrestrial life, and the future of cosmic exploration. Each of these topics reflects our enduring curiosity and the desire to understand the cosmos, a journey that is far from over and will continue to shape our understanding of the universe and our place within it. We are made of star stuff. We are a way for the cosmos to know itself. The universe, mysteries and revelations. When we speak about the universe, a majestic picture of space unfolds before us, mesmerizing with its infinity and mystery. The universe is not just a space filled with stars and galaxies, it is an incredibly complex, dynamic, and multi-layered world where every object, from the smallest subatomic particle to giant galactic clusters, plays its role in the grand symphony of cosmic processes. Each aspect of this world hides mysteries whose answers could forever change our